everybody, here is our video on simplifying radicals. So whenever we simplify radicals, you're going to have to remember a few properties of radicals. And we've kind of talked about these before, but write these down so you remember them. And that is if you have different things multiplied under a radical, you can separate them and they each get their own radical and you're going to multiply all the terms. This only works if you have multiplication, not addition. Similarly, if you have two things that are divided, they each get their own radical when they're divided. The last thing that we talked about is if the index and the exponent are the same, they will cancel out, leaving you with just the radicand. So like the cube root of x cubed is just x, because the cube root is the same as x to the 1/3 here, and they would cancel. So let's do a quick review of just simplifying radicals whenever we have a number, because it's really similar. What we're eventually going to do is have a radical and have a bunch of variables under here raised to powers that we need to simplify. So let's say your most recent warm-up was simplifying square roots of numbers. We haven't really done cube roots, but just so you get the basic idea again of this, is you're going to do a cube root, and you're going to rewrite this, and you're going to think, what two numbers can I multiply where one of them is a perfect cube? Normally you think, what's a perfect square? But you want to think this time, what's a perfect cube? And in this case, it's 27 and 5. And what we're really doing is we're giving each of these their own radical. And this is what we'll eventually be doing with all variables. The cube root of 27 is 3, and I'm left with 3 times the cube root of 5. Another one is, what if I have the cube root of 104? That could be the cube root of 8 times 13, which is the cube root of 8 times the cube root of 13. And cube root of 8 is a perfect cube, so 2 times the cube root of 13. So that's just a review with numbers. Let's go ahead and do this with variables because that's what we're really interested in. So we're going to do examples that look like this. We'll have a radical with variables under here, variables raised to powers. So there are 3 ways, like I said. I'm going to do them in order from least efficient to most efficient. The last one is the one that you're going to want to lean towards. Really, you can do the whatever way you want, but I would recommend the last way. I'm going to show you, but again, there's usually more than one way to do this. So if I'm going to do a to the 7th, that's the same as a multiplied by itself 7 times. And if I have a cube root, the things that can come out together are triplets. So this would be a times a to a is a cubed. Here's another a times a times a, that's a cubed. They each come out and they each become an a. So this triplet comes out, becomes a. This triplet comes out and becomes an a. And stuck under here is 1a. So there's a cube root of a to the first power. Now a times a is a squared. You multiply the things that escape. So a squared times the cube root of a. That is one thing, or one way to do this. Another way to do this is when you think, all right, I have a to the 7th, and the things that escape perfectly are a to the 3rd. So you're going to rewrite this as a to the 3rd. And you're going to think, okay, how many a to the 3rds do I have in a to the 7th? Well, here's a to the 3rd. You have another a to the 3rd hidden in a to the 7th. So that's 3, 6. I have one more left over, so it's just going to be on its own right here. So 3, 6, 7. So you have 2 a cubes hidden in a to the 7th. And then you think, all right, each of these is just a. Cube root of a cubed is just a. So I have a times a. And then this one you can't do anything with. And the reason you can't do anything with it is the exponent is smaller than the index. And you end up with the same answer. Obviously, I was expecting that. These 2 ways are really the same exact idea. It's just here you're writing it out all the way. And here you're writing them as powers that are the same as the index so that they cancel. Like that. Now, here's how I usually do it. I usually think, okay, I have 7 and an index of 3. So I'm going to do 3 divided into 7. And I think, all right, what is the most that 3 can go into 7? The most it can go into it is twice. And the reason it's twice is because it's 6 over 3 times 1 over 3. So you break up 7 and you break it into the number that is divisible by 3, the biggest number divisible by 3, and then you write the remainder over the index as well. Well, a to the 6 over 3 is a squared, and then I'm left with the cube root of a. So basically, you just do the exponent divided by the index, and whatever that number is, it's your exponent on the outside, and then whatever the remainder is left as an exponent under the radical. Make sure you write this down here. This is how you know that you're done. You're done when your exponent that's under the radical, so like this one right here, is less than or equal to the index, which is right here. So for example, let's say you had done this problem out and you had gotten a times the cube root of a to the fourth. Well, here my exponent is not less than or equal to my radical, and the reason it's not done is because there's another perfect cube under here. There's an a cubed under here that needs to come out as well to get the final answer. Let's do two examples that combine what we just did with the numbers and the variables here. And you can have numbers and variables together. You just have to remember to treat the numbers as numbers and the variables as variables. Don't do the same thing for them. Make sure you wrote this note down for yourself before you move on to the examples. So I'm going to do these examples different ways. I'm going to be trying each of the different methods so that you can decide which one you're more comfortable with. So what I'm going to do for this one is the first method that I showed you, which is not necessarily the most efficient, but visually it helps a lot. So I have a square root. That means my index is 2. That means I need twins to come out or couples to come out. So x squared can come out. 25, which is really 5 times 5, can come out. Y squared can come out. And, oh, look, another y squared can come out. So what I'm going to do is I'm going to write out the square root of 25 was 5. This came out to be x. This and this each came out to be a y. Stuck under my square root is this 2 and this x. So my final answer is 5xy squared times the square root of 2x. Sometimes you'll have a radical left over. Sometimes everything will escape. Okay, let's try this one. Now, sometimes what some people like to do, instead of writing it all out in a prime factorization, by the way, this is the prime factorization. That's like the more technical way of saying writing it all out. So anyway, some people like to write it with a bunch of radicals, giving each term its own radical. Visually, it helps them to do this, and that's fine if you do it that way. So I need two numbers that multiply to 192, where 1 is a perfect cube this time, and let's see, that would be 64 times 3. And then what some people like to do, well, cube root of x cubed is just x. And then this is y to the fourth right here. So some people say, okay, the biggest perfect cube under here is, there is one y cubed under here. And then what's left over is just y to the first, because 3 plus 1 is 4. So then cube root of 64 is 4 times the cube root of 3. Then there was this x. Cube root of y cubed is y. And then I have the cube root of just y to the first. Now your final answer should only have one radical. So I'm going to take everything that escaped and bring it out front so it looks a little neater. Everything that's still under a radical should go under it together, like that. And there's your final answer. Make sure your index doesn't look like an exponent on the terms on the outside. It's not y cubed, it's the cube root. I'm going to do a few more examples with you, getting increasingly more difficult. So let's start with these three here. They're pretty entry level. And I'm going to do method 2 with them, and then I'm going to start doing the more efficient method so you can see how to do it more quickly. If I have the cube root of 64y to the 6th, what I can do is give each of these their own radical, and then I'm going to tackle them separately. So the cube root of 64 is perfect. It is 4. The cube root of y to the 6th, I'm going to break up 6 into as many cubes as I can. Oh, check it out. 3 and 3 is 6. I already used it all up. And look at these. Each of these is perfect. Each of these ends up being y. So I have 4 times y, 4y squared. So sometimes that'll happen if everything's a perfect cube. If I change this exponent to a 5, your answer ends up being different because 5 is not a perfect cube. So I break them up separately. Cube root of 64 is 4. I'm going to take 5 and write it into as many perfect cubes as I can. So there's 1. And then what's left over is 2, because 3 and 2 is 5. Alright, so the cube root of y cubed is y. I can't do anything with the cube root of y squared because my exponent is less than my index. So there's my final answer. Let's try this one here. Cube root of 27, cube root of p cubed, cube root of q to the 7th. Well, cube root of 27 is 3. Cube root of p cubed is p. Let's take 7 and write it into as many perfect cubes as we can. There's 3. There's 6. I have 1 left over. 1 more. So that is 3p q, q, cube root of q. So your final answer is 3p q squared, cube root of q. So pause the video and make sure you have all the stuff written down. I'm going to do a couple more examples now. For this example right here, I gave each term its own cube root. And I'm going to tackle them separately here. The 81 is not a perfect cube, but I'm going to think of it as 27 times 3. And 27 is a perfect cube. Cube root of a to the 6. So I'm going to start doing the more efficient method, which is method 3, where you take your exponent and divide it by the index. Okay, so 6 divided by 3 is 2. 9 divided by 3 is 3. They each have no remainder, so they're perfect cubes. So anyway, I had a cube root of 27 times 3. That turns into 3 times the cube root of 3. Cube root of a to the 6th is just a squared. Cube root of b to the 9th is b cubed. So my final answer is 3a squared b cubed, cube root of 3. I usually put the radical at the end. You don't have to, but it's usually a good idea. Now, sometimes you're going to get your example and you're going to have separate radicals. I would recommend writing everything under one radical, and that way you only have to simplify once. You could do them separate, but then you'd have to combine things at the end. I find it to be easier to combine now. So I just added all my exponents of my like terms, and then like for my numbers, I just did 8 times 2 is 16. Don't add 8 and 2. You multiply them to be 16. So this is how I usually think of them. It's the quicker way. I do the 4th root of 16. Is that perfect? It is. It's just 2. The 4th root of x to the 4th. Well, 4 divided by 4 is 1. No remainder. 4th root of y to the 9th. 9 divided by 4 is 2 with 1 left over. And then here I have, and here again, 9 divided by 4 is 2. And then I have the 4th root of z to the 1st left over. So I'm going to combine it into one radical. So here's my final answer. I put everything in the front that was out of the radical, and I put all the radical stuff together. All right, let's do this one here. Let's try the cube root of 250, x to the 4th, y to the 5th, z to the 6th, w to the 7th. Now, you might be thinking, oh, that's a lot. But if you do the shortcut way, it's really not that bad. I'm going to do the cube root of 250, and let's see, I need a perfect cube. Let's do 125 times 2. So the cube root of 125 is 5, with the cube root of 2 left over. All right, x to the 4th, I need a cube root of that. Well, 4 divided by 3 is 1, with a remainder of 1. 5 divided by 3 is 1, with a remainder of 2. 6 divided by 3 is 2 with no remainder. 7 divided by 3 is 2 with 1 remainder. So let's clean it up. Here's the final answer for the previous one. All right, one more example. Let's try one that looks like this. And sometimes you'll get examples that look similar to this one here. You just have to realize that raised to the 1/4 is the 4th root for both of them. So I'm going to combine everything that's under each of these radicals. And so that means 9 times 18 is 162. A to the 6th times a squared is a to the 8th. B to the 11th times b is b to the 12th. Then I have a c to the 20th. D times d is d squared. So 162 is 81 times 2. The 4th root of 81 is 3. I'm left with a 4th root of 2. And then 8 divided by 4 is 2. 12 divided by 4 is 3. 20 divided by 4 is 5. These are all perfect. And then 2 divided by 4, well, my exponent's smaller than my index, so it has to stay under there. So this ends up being your final answer when you combine your numbers on the outside and radicals on the inside. So I'm going to give you a set of problems to try. So make sure you have all the examples written down, and I'm going to put up your homework problems. So here is a set of 10 homework problems to do. Write these in your notebook, write the original problems down with them, and we'll go over them next time I see you. Bye.